Hello, hello, National 5 chemists. It's Mr. Morton here. I hope you're all doing really well. Here is our third and final lesson on nuclear chemistry. We're looking at half-life today and some kind of numeracy based questions really around half-life. Nothing too difficult. If you can divide by 2 and multiply by 2, this is quite straightforward, and trust me, it is as easy as that.
Dangerous radioactive substances will not be dangerous forever. Over time, radioactivity can make substances more stable and far less hazardous to humans. In order for an unstable isotope to become stable, its nucleus must change, and it does this by emitting radiation. This is called radioactive decay, and the process leaves behind a completely different element. The new element will probably also be unstable, but then the process repeats in what becomes a decay chain, until, eventually, a stable element remains. When this unstable isotope, molybdenum-99, decays, beta radiation is released, and it becomes technetium. The technetium then emits gamma and beta radiation to become ruthenium-99, which is stable.
If I'd been holding this amount of molybdenum perhaps 6 months ago, it would have been extremely dangerous for me. However, in that 6 months, it's decayed away and I can safely hold it.
How do we know when a radioactive substance will cease to be dangerous? Scientists determine this by calculating a substance's half-life, the time it takes the radioactivity of a substance to decrease by half. This isotope of molybdenum has a half-life of around 3 days. So if you had 20 grams of molybdenum, after 3 days you would have only 10 grams. In another 3 days, only 5 grams, and so on until no more radiation is being emitted, and only a harmless, stable element, ruthenium, remains. Different materials have different half-lives. Half-life can be anything from fractions of a second to millions of years. Knowing the half-life of a substance helps us to safely store radioactive waste until it no longer poses a health risk.
What is half-life then? Well, for any radioactive substance, that radioactive substance will decay, and it will decay in a standard way. Every single radioactive substance will decay with a graph very similar to this graph here of technetium-99. And essentially all a half-life is the time it takes for the mass of a radioactive substance to be halved. So if I look at this graph here, where I've got 1 gram of my radioactive substance, half of 1 gram is half a gram. So the time taken to go from 1 to 0.5 on the graph is 6 hours. And that is the half-life, that's it. It doesn't matter how much mass I have. I could have 1,000,000 grams here, and the time it takes to go from 1,000,000 grams to 500,000 grams is going to be 6 hours, because the half-life is always the same for each individual radioisotope. So what I mean by that, it won't always be 6, but the half-life, no matter what the mass is, will always be the same quantity of time. And we can see that again here. If I go from 0.5, half of 0.5 to 0.25, there's 0.5 in the graph, there's 0.25 in the graph, it's taken another 6 hours. And we could do it again and again and again, and we can go on forever. If we wait 6 hours, the mass of this radioisotope will halve every 6 hours, no matter what mass it is. And that's all that half-life is. That's all it is. That's just describing how long it takes for the mass of a radioactive substance to be halved. And there's some information inside there, just explaining exactly what I've just said there. It takes 6 hours from for our technetium 99 to fall from 1 gram to half a gram. Doesn't matter how much of it we have, it's always going to be 6 hours for this particular isotope. It won't be 6 hours for every single radioactive isotope, but for this one it is always going to be 6 hours. And here's a definition that I'd like you to remember. Half-life is the time taken from the mass or activity of a radioisotope to half. That's it, just the time it takes to be halved. Now, just before we get in to look at half-lives in a little bit more detail and some numeracy questions around them, it's important to note that we can't really affect the rate of a half-life by our traditional means of speeding up a chemical reaction. So what I mean by that is, if I increase the temperature, increase the pressure, add a catalyst, it's not going to have any effect on the half-life. The half-life and the radioactivity of any element or radioisotope comes from the nucleus, and we cannot affect the nucleus by stuff like temperature and pressure and adding catalysts like we would normally do on a chemical reaction. So the half-life is just, we can't really alter it. And the half-life is constant for a particular isotope. Like I've said, it doesn't really matter what state it's in, doesn't matter how much of a substance I have or the temperature. Like I've said, if I have got 5 grams of this carbon-14 isotope, the half-life of those 5 grams to go from 5 to 2.5 is going to be the exact same time it takes to go from 40 grams of the exact same isotope to 20 grams. So it doesn't matter how much I have, that half-life is always going to be the same. I could have 1 gram, could have a million kilograms. To go from 1 to half and a million kilograms to half a million kilograms, it's going to be the exact same time. And additionally to that, it doesn't actually matter if we take this radioactive element and put it in a compound, it'll have no effect upon the half-life as well. So if I took this radioactive lead and I looked at its half-life, it's going to be the exact same as if I took the same lead and put it in a compound with chlorine. It's going to have the exact same half-life. I can't really affect it. And the reason for this is we're normally used to affecting chemical reactions by affecting the electrons. And when we're talking about radioactivity here with half-life, with our alpha, beta, gamma radiation, we're all concerned with the nucleus of an element, the nucleus of an atom, not so much the electrons on the outside. So our normal techniques for speeding up, slowing down a reaction don't have any effect here. Now that's a very rushed and whistle-stop tour of half-life, and it's mainly because I want to get into the examples, and it's not really something that you have to know a whole lot about. Is the actual theory behind the half-life. As long as we know it's just the time taken for a sample to half and its radioactivity or its mass, then that's fine. What we're more concerned with is these kind of numeracy examples where we've been given a problem here, we've been told how long the half-life is, and we want to work out how much is left after a specific time, or maybe sometimes we want to work out what the half-life is. So for this question here, it says that we've got 100 kilograms of a radio isotope with a half-life of 2.5 years. They buried it and left it for 10 years. What mass of the original sample will remain? So we know that half-life, and that is just a wee shorthand for writing half-life, small case t and a half, is equal to 2.5 years. And they buried it for 10 years. So I want to know how many half-lives are going to occur within this 10-year period. So how many times is this 100 kilograms going to be halved? So in 10 years, if I divide that by 2.5 years, we'll figure out that there's going to be 4 half-lives within that 10-year period. Each half-life, remember, was 2.5 years, so I can fit 4 half-lives into that 10-year period, which then tells me that, well, if I'm starting with 100 kilograms and I leave it for 10 years, that 100 kilograms is going to half 4 times. So here's our first half-life. If I leave it for the first 2.5 years, then it's going to go from 100 to 50. Let's do our second of the 4 half-lives. It's going to go from 50 now to 25. That's me after another 2.5 years. 5 years in total, but we're leaving it for 10 years. Let's do another 2.5 years, another half-life. Scroll down the page a little bit, and we're halving that 25 again to 12.5 kilograms. So we have left this for a total of 7.5 years. Let's do one more, our fourth half-life. So we've got our 10-year period, and we've got our final answer of 6.25 kilograms. So in total, we've left it for 10 years. We calculated that in that 10 years, we'd have 4 half-lives. There's 1, there's 2, there's 3, and there's 4. So from the 100 kilograms that we started with, we are going to end up after 10 years with only 6.25 kilograms, and that would be our final answer to the question. Let's look at our second example here, very similar in the way that we're going to approach this. We've been told that we're starting with an 80-gram sample of a radioisotope phosphorus. That phosphorus has a half-life of 14 days, so every 14 days, no matter what mass I have, it will be halved. Calculate the remaining mass of the sample after 56 days. So I know that my half-life is equal to 14 days. I'm leaving the sample for 56 days. So how many 14s in 56? Well, the answer is 4. So I'm again going to have 4 half-lives for this sample during the 56 days. I'm starting out with 80 grams, and I'm going to half it once to 40, going to half it twice to 20, a third time to 10, and finally to 5. So if I leave this for the total of 56 days, we know that there's 1, 2, 3, 4 half-lives within the 56 days. So I'm going to half my 80 kilograms 1, 2, 3, 4 times. And what will I be left with at the end? Well, I'll be left with 5 grams if I started with 80. Let's look at our third and final example here, just doing it the opposite way around. This time we're not asked to calculate how long is left after a time period, we've been asked to calculate what is the actual half-life. So we've got a radioactive isotope with an activity of 200 counts per minute. It's kept for 40 minutes and the count rate drops to 50 counts per minute. What is the half-life of this isotope? So we know that we are starting with 200 counts per minute. If I half that, I will get 100 counts per minute. If I half that again, I'll get 50 counts per minute. And I'm going to stop there because I know that that's what the counts per minute was after the 40 minutes. So I say, how many times have I halved this 200? Well, there's one half-life. There's our second half-life. So I've halved the 200 twice. There's been 2 half-lives within the time period that I left the sample. The sample was left for 40 minutes. So if this entire time here was 40 minutes, then it would stand to reason that within those 40 minutes, if I'm getting 2 half-lives, each half-life must have a time of 20 minutes. And we can check that. I'm starting at 200. After 20 minutes, I've done 1 half-life, and I've got 100. After a second 20 minutes, I'll have done the total of 40. I'll have done a second half-life, and I'll be left with 50 counts per minute. And our answer then, well, half-life must be 20 minutes.